Hello friends, this is Gurleen Singh from Infinity Vision. In this video we'll be discussing NCERT solution of relations and functions, which is the first chapter of class 12 test book. So we'll be discussing the first exercise in this video, which is exercise 1.1. So let's move on. Let's see the first question. So the first question is, determine whether each of the following relations are reflexive, symmetric and transitive. And in this slide, I'm just discussing the first part of this question. So in the first part, relation is given as, in set A, these are all the elements. These are all the elements, 1, 2, 3 up to 14. Okay, and the relation is defined as 3x minus y is equal to 0. So first we have to check which all pairs will come in this relation. So let's see. First we have, if x is equal to 1, then y will be equal to 3, because 3x is equal to y in this case. So therefore 1 comma 3 will be a set in this relation. Similarly, we have 2 comma 6, which will be also present here, since if x is equal to 2, then y is equal to 6. So we have 2 comma 6. Similarly, if x is equal to 3, y will be equal to 9. We have 3 comma 9. And finally we have x is equal to 4, then y is equal to 12. So we have 4 comma 12. So there are no possible sets available except these 4. Okay, तो इनमें देखते हैं कि ये relation reflexive, symmetric और transitive है या नहीं. Okay, so for reflexive we have to check that every element x is related to itself. Okay, but in this case, for reflexive, to check for the reflexive property, 1, 1 is not present, 2, 2 is not present. Similarly, 14, 14 is not present. Therefore, this relation is not reflexive, since 1, 1, 2, 2 up to 14, 14, they don't belong in R. Therefore, this is not a reflexive relation. To check for symmetric relation, we have to check that if 1 comma 3 is present, then 3 comma 1 should also be present. Okay, in symmetric we have to check if x comma y is present in this relation, then y comma x should also be present. So for that we check if 1 comma 3 is there in R, but 3 comma 1 is not present in R. Therefore, symmetric property is not satisfied. Therefore, this relation is not symmetric. Then we have to check for transitive. Now we can see that 1 comma 3 is present in this. Similarly, 3 comma 9 is also present. So for transitive, we have to check if xy is there and yz is there. Therefore, xz should also be there. But in this case, 1 3 is there, 3 9 is there, but 1 9 is not there. Therefore, this is not transitive. So this first relation is neither reflexive, nor symmetric, nor transitive. So let's move on to the next question. So in the next question, we can see that the relation is defined as y is equal to x plus 5, where x is less than 4. So for this, let's first make the relation. Let's first make the relation, and we'll see that R will have these all sets. So first will be 1 comma 6, since the value of x is less than 4 and y is x plus 5, and it is all natural numbers, so we'll start with the first natural number, which is 1. So the first set will be 1 comma 6, second will be 2 comma 7, third will be 3 comma 8. Now let's see if this is reflexive, symmetric or transitive. For reflexive property, we have to check whether 1 comma 1, 2 comma 2, 3 comma 3, these are present or not. But we can clearly see that 1 comma 1, 2 comma 2, 3 comma 3 are not present. Therefore, this is not a symmetric, reflexive relation. Now let's check for symmetric. So for symmetric property, if 1 comma 6 is there, 6 comma 1 should also be present in the relation, which is not true. Since 1 comma 6 is present, but 6 comma 1 is not present. Therefore, this is not symmetric. Now let's check for transitive property. Now for transitive property, we have if A comma B is present and B comma C is present, then C comma A should also be present. But in this case, we can see that 1 comma 6 is there, but 6 comma something is not there. Since x comma y is there, y comma z is not there. Therefore, this is not transitive as well. So we have to check for all these properties: reflexive, symmetric and transitive. So let's move on to the next question. Next is relation R in the set A is equal to, the set A is given as 1, 2, 3, 4, 5, 6, and XY is a relation such that y is divisible by x. Now this is a very interesting question. For just a second. For reflexive property, we have to see if x comma x, which means 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5, 5, 6, 6, these are present or not. Now we see that x is divisible by x. Now this we all know, every number is divisible by itself. Therefore, x comma x belongs to R. So therefore, this relation is reflexive. So reflexive property is satisfied. Similarly, we'll see for symmetric property. Now if y is divisible by x, then x can't be divisible by y unless they're both equal. So we'll understand this by an example. For example, we have 2 comma 4. Now 2 comma 4 will belong to this relation since 4 is divisible by 2, but 4 comma 2 does not belong to this relation since 2 is not divisible by 4. Now 2 completely divides 4, but 4 does not completely divide 2. Now we'll check for, so this is not symmetric. Now we'll check for transitive relation. For transitive, we'll see, for example, if we have 1 comma 3, this belongs to R, and 3 comma 6, this belongs to R, which means 1 divides 3, or 3 is divisible by 1. Similarly, 6 is divisible by 3. Then this implies that 6 is divisible by 1. So we will have 1 comma 6 also in this relation R. So this satisfies the transitive property of relations. So therefore this relation is reflexive and transitive but not symmetric. So let's see the next question. Next question is, relation in the set Z of all the integers defined as x minus y is an integer. Okay. So first we'll check for reflexive property. So x comma x will belong to R. Why will this belong to R? Since x minus x is 0, which is an integer. Okay? So this satisfies the reflexive property. So this is true. Similarly, if we have for symmetric property, let's take an example. Let's suppose we have 1 comma 3. Now we can see that this belongs to R because 1 minus 3 is minus 2. Now this is an integer. So therefore 3 comma 1, this will also belong to R because 3 minus 1, which is nothing but the negative of this number, will also be an integer. So both of these numbers will be integers. So therefore this will satisfy the symmetric property. Now we'll check for transitive property. Now for transitive property, let's suppose we have a comma b, which belongs to R. Okay. Similarly, we have b comma c, which belongs to R. So this means a minus b, this is an integer. Similarly, b minus c, this is also an integer. So therefore the sum of two integers will also be an integer. Therefore this is also an integer. Therefore a comma c also belongs to R. Since a comma c is nothing but a minus c, which can be obtained by adding these two. So therefore this is also a transitive relation. So this relation is reflexive, symmetric as well as transitive. Therefore this will be an equivalence relation. So let's move on to the next question. So next question has multiple parts. So fifth question has cut. क्या दे दिया? ठीक ठीक है. हाँ हाँ. वो कहाँ गया? ये अपने आप ये वाला शुरू हो जाता है, ये जैसे नेक्स्ट स्लाइड करो ना, तो ये वाला इसकी जगह ये वाला आ जाता है, येलो वाला। हाँ ठीक है। सो दिस फिफ्थ क्वेश्चन, सॉरी फिर से कट। So the fifth part of the first question has multiple parts, multiple subparts. So we'll see the first part in this. So A says X and Y work in the same place. Okay. So this is this relation in set A of human beings in a town at a particular time given by this. So we have a set A of human beings, normal people. Now we have a relation that X and Y work at the same place. Now let's see if we have the condition for reflexive property, this will be satisfied since X and X, they will work at the same place. Since X will work with himself, right? They are working in the same place, it's the same person. Okay, this will belong to R. So this is a reflexive relation. Now we'll check for symmetric relation. Since X and Y belong to R, if X and Y work in the same place, then Y and X will also work in the same place. This is pretty obvious. Therefore, both of these will be valid relations. So therefore, this is a symmetric relation as well. Now let's check for transitive relation. If X and Y work in the same place, Y and Z, they also work in the same place. That means X, Y, they are working in the same place. Now Z is working in the same place as Y. Therefore, X, Y and Z, all three, they are working in the same place. Therefore, X and Z, they will also work in the same place. So therefore, X and Z will also belong to R. So therefore, this is also a transitive relation. Subsequently, let's move on to the next part. Next part is B part, which is X and Y live in the same locality. Okay, this is also quite similar to the previous one, but we'll anyhow do it. Now, let's see for reflexive property. X and X, they will live in the same locality because it's the same person. It's quite similar to the previous question. Therefore, X and X belongs to R. So therefore, this is a reflexive relation. For symmetric, it's the same thing. If X and Y, they live in the same locality, then Y and X, they will also live in the same locality. So therefore, this is also a symmetric relation. Hence, this is also true. Now we'll check for transitive property. If X and Y live in the same locality, similarly Y and Z live in the same locality. Therefore, X, Y and Z, all three will belong to the same locality. So therefore, X and Z also belongs to R. So therefore, this is also a transitive relation. So therefore, this is an equivalence relation. Reflexive, symmetric and transitive. Let's move on to the C part of this. Now let's see the C part of this. X is exactly 7 centimeters taller than Y. So first, we'll check for reflexive property. So for reflexive property, we'll first see if X is related to X itself. Now this is not possible because the same person cannot be 7 centimeter taller than himself. Therefore, this does not belong to R. Since X cannot be 7 centimeter taller than X. So this is not reflexive. Let's check for symmetric. If X is exactly 7 centimeter taller than Y, then Y is 7 centimeter shorter than X. Okay? So if the height of X is Y plus 7, then the height of Y is X minus 7, not plus 7. Therefore, this does not belong to this relation. Therefore, this is not symmetric. Let's check for transitive. If XY belong to R and YZ belong to R. So this means X is equal to Y plus 7 and Y is equal to Z plus 7. Now in this case, if X is Y plus 7, Y is Z plus 7, if we substitute the value of Y over here, we get X is equal to Z plus 14. So therefore X is 14 centimeter taller than Z, which is not true for this relation. Therefore this is not transitive as well. So let's move on to the next one. So the next one is relation XY such that X is the wife of Y. So let's first check for reflexive property. Now X and X will not be a part of this relation, since X cannot be the wife of X itself. So therefore, this is not a part of this relation. Now we'll check for symmetric property. If X is the wife of Y, then Y is husband of X. Okay? So therefore, YX does not belong to R. Right? So therefore, this is not a symmetric relation. Now we'll check for transitive relation. Now if XY belong to R, that means X is wife and Y is the husband. So in transitive we have XY and YZ. Then we determine XZ. If YZ also belongs to R, this is not possible. Since Y is the husband, then Y cannot be the wife of Z. Therefore, this does not belong to R. Since this is female, this is a male. Now Y cannot be a female if he is a male. Therefore, YZ does not belong to R. So therefore, this is not a transitive relation. Similarly, let's check for the next one. So the next one is XY such that X is the father of Y. Let's check for reflexive property. X is the father of X. This is not true. Since if X is the father of Y, Y will be either son or daughter of X. So therefore x comma x does not belong to R. Therefore this is not a reflexive relation. Now we have property for symmetric relation. For symmetric we check if xy belong to R, which means x is father of y, then yx does not belong to R since y is son slash daughter of x. So therefore this is not a symmetric relation. Now let's check for transitive relation. In this case, if xy belongs to R, this means x is father of y. Similarly, if yz belongs to R, this means y is father of z. Then we have to check if either xz also belongs to R. But this is not true. Since if we have x as the father of y, y as the father of z, therefore x will be grandfather of z. Does not belong to R because x is grandfather of z. Therefore this is not a transitive relation. So we are done with the first question. Let's move on to the second question now. So the second question is, show that the relation R in the set R of real numbers. So don't confuse with both of these R. This is R for relation and this is R, the set of real numbers. So the relation is defined as AB such that A is less than or equal to B square. Is neither reflexive nor symmetric nor transitive. So we have to prove that this is neither of these. So we'll check for reflexive property. For reflexive property, it's pretty obvious. Let's take an example, 2, 2. So if we see 2, 2, both are real numbers, right? Now if we check 2 is less than or equal to 2 square, this is true. 2 is less than or equal to 4. Therefore 2, 2 exists in this set, in this relation. Now if we check 1 by 2, 1 by 2, this becomes a little tricky. Since the square of a number which is greater than 1 is greater than the number, okay? But if the number is less than 1, lies between 0 and 1, then the square of the number becomes less than the given number. Okay, so if we take the square of 1 by 2, it becomes 1 by 4, which is actually less than 1 by 2. Therefore this is not a reflexive relation. Now we'll check for symmetric relation. So this is pretty obvious, symmetric relation. If we have, let's suppose 2, 3. So we'll have 2 is less than or equal to 9. So this is true. Therefore 2, 9 belong to R. Sorry, 2, 3. But if we take 3, 2, we take 3 less than or equal to 2 square, which is 4. So this also satisfies. Therefore 3, 2 also belongs to R. So this is one case. We're discussing one case where this is true and another case where this is not true. Okay. So let's take another example. Let's say we take 1 comma 2 in this case. So we have 1 is less than equal to 4, which is true. But if we take 2 comma 1, so 2 is less than equal to 1, this is not true. So therefore 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. So therefore this is not a symmetric relation as well. Now we'll check for the transitive property. So I'm going to clear the screen for that. So for transitive property, we can take an example like, let's suppose we have three comma 2. Now this will belong to R since 3 is less than equal to 4. So this is true. Next, let's suppose we have 2 comma 1.5. So for this we'll check if 2 is less than equal to 1.5 square, which is nothing but 2 is less than equal to 2.25, which is also true. Therefore 2 comma 1.5 also belongs to R. For transitive property, if AB is there, BC is there, we have to check for AC. So for AC, we take 3 comma 1.5, which does not belong to R, since 3 is not less than equal to 2.25. Okay? So therefore, this is not a transitive relation. Therefore, we proved that this is neither reflexive nor symmetric nor transitive. Okay? So let's move on to the next slide and see the next question. So the next question is, check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as B is equal to A plus 1 is symmetric, reflexive or transitive. So let's first check for reflexive property. So for reflexive property, we have to check for A comma A, if A comma A is present in this. So if we consider A comma A, then A is not equal to A plus 1. Therefore, this is not a reflexive relation. Now we'll check for symmetric relation. So if A comma B is present, so in this case this did not belong to R, therefore this was not reflexive. For symmetric, if A comma B is present, then B is equal to A plus 1. And if B comma E, we check for B comma A, then this will not be true. Since A plus 1 is equal to B, this A will be equal to B minus 1, not plus 1. Therefore, B comma A does not belong to R. This is not a symmetric relation. Let's check for the transitive property. If A comma B is there and B comma C is there, which means B is equal to A plus 1 and C is equal to B plus 1. Then what will be the relation between C and A? If we substitute this value of B over here, we get C is equal to B, which is nothing but A plus 2. Now instead of A plus 1, we are getting A plus 2. Therefore, this is not a transitive relation since A comma C does not belongs to this relation. Hence, this is not reflexive, not symmetric, not transitive. Let's move on to the next topic. Next question. So in this we have relation which is defined as A is less than equal to B. So for reflexive property, it's pretty simple. A comma A belongs to R since A is less than equal to A. Now A is not less than A, but A is equal to A, which is one of the condition of this inequality. Therefore, this is a reflexive relation. Now let's check for symmetric relation. If we have A comma B, which belongs to R, this implies that A is less than equal to B, which further implies that B comma A will not belong to R. Since B comma A means B is less than equal to A, which is not true. If A is less than equal to B, then B will be greater than equal to A. Therefore, this is not symmetric. Now let's check for transitive property. Now if B belongs to R, therefore A less than equal to B. If BC belongs to R, that means B is less than equal to C. Now from both these inequalities, we can infer that A is less than equal to C. Since A is less than equal to B, B is less than equal to C, these both imply that A is less than equal to C, which means A comma C belongs to R. So therefore this is transitive and reflexive but not symmetric. So this was what we had to show in this question. So hence proved, and let's move on to the next one. So next one is similar to the question we did. In that case we had square, but we have cube over here. So let's see if this satisfies the reflexive property. For reflexive property, A less than equal to B cube. Let's suppose we have 1 by 2 comma 1 by 2. So it's the simplest example we can get in such type of questions. So for 1 by 2 comma 1 by 2, we have 1 by 2 is less than equal to 1 by 8, which is not true. Therefore 1 by 2 does not belong to R. Now this relation R is in R, which means this R means real numbers. So we have to check for all the real numbers. Negative, positive, fractions, all real numbers. So one example we had in which this is not satisfying. Therefore, this is not reflexive. Let's check for symmetric. So it's pretty simple for symmetric as well. Let's suppose we have 1 comma 2. Now this belongs to R since 1 is less than equal to 8. Okay. Similarly, if I see 2 comma 1, then 2 is not less than equal to 1, which means this does not belong to the relation. Therefore, this is not symmetric. Now let's check for transitive property. For transitive property, let's take an example 3 comma 3 by 2. Let's see if this belongs to R. So for this transitive property, I'm going to need more space. That's why I'm going to clear the screen first. So for transitive property, we took 3 comma 3 by 2. Three comma 3 by 2. Now this will belong to R since 3 is less than equal to 3 by 2 cube. Now 3 by 2 cube will come out to be 27 by 8, which is greater than 3. Since 3 is 24 by 8, this is 27 by 8. So this property is true. Let's see another example, 3 by 2 comma 6 by 5. This will also belong to R. Since 3 by 2 is less than equal to 6 by 5 whole cube. So you can check this condition will satisfy. Now if we have A, B, B, C, we have to check for AC. Now we'll check if 3 is less than equal to 6 by 5 whole cube. Now this is not true since 3 will be greater than this number. This number is 1.2. If we take 1.2 cube, it will come out to be 1.728. Okay. So therefore, this is not true. This does not belong to R. Therefore, this is not a transitive relation. Okay. So we checked for all three properties, reflexive, symmetric and transitive. This is not a transitive relation. Let's move on to the next one. So next one is, show that the relation in the set 1, 2, 3 given by 1, 2, 2, 1 is symmetric but neither reflexive nor transitive. So this is a very simple question. Since 1, 1, 2, 2, 3, 3 are not in R, this is not a reflexive relation. Since for reflexive relation, every element in this set should be related to itself. So therefore, this is not a reflexive relation. Next, let's check for symmetric relation. 1, 2 is there. 2, 1 is there. So we have 1, 2 and we have the reverse of 1, 2 which is 2, 1. If both are present, therefore this is a symmetric relation. So this is a symmetric relation. Reflexive relation, it is not. Let's check for transitive. For transitive relation, we can see that we have 1, 2 and 2, 1. So by the transitive property, if we have 1, 2, 2, 1, then 1, 1 should also be present in R. But 1, 1 is not present in R. Therefore, this does not satisfy the transitive property. So it is not reflexive, not transitive, but only symmetric. Okay. Let's see the next question. So 7th one is, show that R in the set of all the books, in the set A of all the books in a library of a college given by R is equal to XY, X and Y have same number of pages. So this is important, is an equivalence relation. So for equivalence relations, let's first check for reflexive relation. First we'll check for reflexive property. X, X will belong to R because the number of books of X will be equal to the number of books of X. Okay. So therefore this satisfies the reflexive property. For symmetric property, we have if X, Y belongs to R, it means number of books of X is equal to Y. This implies that number of books of Y will also be equal to X, which implies that Y, X also belongs to R. Okay, so therefore this is also a symmetric relation. Now we'll check for transitive relation. If xy belongs to R, yz belongs to R, it means x is equal to y and y is equal to z, which implies that x is equal to z also. Therefore x is equal to z, which means x comma z also belongs to R. So this satisfies the transitive property, reflexive property, symmetric property. So relation in which all these three properties are satisfied is called an equivalence relation. So therefore this relation is an equivalent relation. Let's check for the next question. Show that the relation in the set 1, 2, 3, 4, 5. So this is the set which is given to us, and the relation is given A minus B mod is even, is an equivalence relation. Show that the elements of 1, 3, 5 are related to each other, elements of 2, 4 are related to each other, but no element of 1, 3, 5 is related to any element of 2, 4. Let's first prove that this is an equivalence relation, then we can move to the second part. So to prove that this is an equivalence relation, first we'll have to check for reflexive relation, like we've been doing in all the questions. So A comma A belongs to R. This is true since A minus A modulus is equal to 0 and 0 is even. Therefore this is a reflexive relation. Let's check for symmetric relation. If A comma B belongs to R, this means mod of A minus B is even. Then B comma A also belongs to R, since B minus A can be written as minus of A minus B. And if we take the modulus of this negative sign, it will be removed. Therefore this becomes mod of A minus B, which we have seen that it is even. Therefore this is also a symmetric relation. Now let's check for transitive relation. If A comma B belongs to R, that means A minus B mod is even. Let's say this is 2k. Similarly, if we have B comma C, this belongs to R, okay? Then B minus C is equal to 2, let's say P. Now if we see A minus C, for A minus C we have to check whether mod of A minus C is an even number or not, okay? So this we can check in two cases, whether if B is greater than A and C is greater than B, or whether A is greater than B or B is greater than C. So in both these cases, this A minus C will come out to be the sum or difference or both negatives of these two numbers. So we will have plus minus 2k plus minus 2p in all these cases. Since this has to be positive in all these cases, but mod A minus C is not exactly the sum of these two. This will come out to be either plus minus 2k or plus minus 2p. So therefore, since this is sum of two even numbers, therefore this is also a even number. So therefore This is also a transitive relation. You can either split this as A minus B plus B minus C. Okay, we can do that. But for that, we'll have to separate the modulus. So for separating the modulus, we need to be clear that this K and P, these are positive or not. Okay. So let's see the second part of this. So for second part, we have to show that elements of 1, 3, 5 are related to each other. So this is obvious since 1, 3, 5 is set of odd numbers. And we know that the difference of two odd numbers is even. So therefore, all the elements of 1, 3, 5 are related to each other. We can also check if we take 1 and 5, then we get mod of minus 4, which is 4. Similarly, if we take 5, 3, then mod of 2, it is also even. Therefore, all the elements of 1, 3, 5 are related to each other. Okay. Similarly, we have 2, 4. Now in 2, 4, this is a set of both even numbers. Therefore, the difference of two even numbers is obviously an even number. Therefore, all elements of 2, 4 are related. Let's see if we have 1, 3, 5 and 2, 4 and they are related to each other or not. So this will not be true. Why? Let's see. Let's take one element from 1, 3, 5 and another element from 2, 4. Let's say we take 5, 2. Now the difference of 5, 2 comes out to be modulus of 5 minus 2, which is 3, which is not an even number. Therefore, set of 1, 3, 5 is not related to set of 2, 4. Therefore, we have proved that this is an equivalence relation. All the elements of 1, 3, 5 are related to each other. Similarly, all elements of 2, 4 are related to each other. But 1, 3, 5 and 2, 4, they are not related to each other. Let's see the next question. So the next question is, show that each of the relation in the set x belongs to z 0 to 12, x belongs to 0 to 12, given by mod a minus b is a multiple of 4, and second is ab is equal to ab relation such that a is equal to b. Both of these are equivalence relation. Find the set of all elements related to 1 in each case. So first we'll solve for the first part. We have mod a minus b is a multiple of 4. So let's see for all the possible examples. So that won't be necessary. Let's see if we can solve it without that. So there will be a lot of cases. We're not going to write that. We're just going to check for the properties reflexive, symmetric and transitive. So for reflexive property we have mod of a minus a, which is 0, which is the multiple of 4. Therefore, A belongs to R. Therefore, this is a reflexive relation. Let's check for symmetric nature. If we have A minus B is equal to 4K, which means A minus B is divisible by 4, then the value of B minus A will also be equal to 4K. Right? Since A minus B and B minus A, they are nothing but negative of each other, but since we are taking modulus, they will both become positive. They will both come out to be 4 comma K. Therefore, these two are equal, and these two satisfy the relation. So if A comma B belongs to R, B comma A also belongs to R. This is also a symmetric relation. Now let's check for transitive property. For transitive property, if we have mod of A minus B is equal to 4K, similarly we have mod of B minus C is equal to 4P, as we did in the previous question, then mod of A minus C will also be equal to some constant times 4. So it will be equal to 4Q. Therefore, if these two are divisible by 4, the third one will also be automatically divisible by 4. So therefore, this satisfies the transitive property. Now let's see the second part of the question, which is find set of all the elements related to 1 in each case. So let's see for the first one, we will have 1 comma 1. Since 1 minus 1 is 0 and it is a multiple of 4. Then next we have 1 comma 5. Similarly 1 comma 9, and that's it. Since we can't have 1 comma 13, the restriction on x is x lies between 0 to 12. So the elements, set of elements related to 1 in each case will be, in this case particularly, the set will be 159. So this will be the set related to 1. Right? So let's move on to the second part, which is quite simple. So for the second part, let's check for the reflexive relation first. We have the relation A is equal to B. Now A comma A will definitely be there, since A is equal to A. So therefore, this is a reflexive relation. For symmetric nature, if A comma B is there, it means A is equal to B. Hence, this also implies that B is equal to A, which implies B comma A also belongs to R. Now let's check for transitive property. For transitive property, we have A comma B belongs to R, B comma C belongs to R. So if A is equal to B, B is equal to C, then we have A is equal to C, which means A comma C also belongs to R. So if AB belongs to R, BC belongs to R, AC will also belongs to R. Now the next part is find the set of all the elements related to 1 in each case. So all the elements related to 1 in each case, in this case, will be just 1, since only 1 comma 1 will satisfy this relation. So set of all the elements will be just this set. singleton set, which is just 1. So let's move on to the next one. 10th question. Give an example of a relation which is symmetric but neither reflexive nor transitive. So these type of questions are very easy. We can just take a common example of a relation. Let's say we have 1, 2, 2, 1, 1, 1. Right? So in this case, 1, 2 is there, 2, 1 is there, 1, 1 is there, but 2, 2 is not there, right? For it to be reflexive, we need to have 1, 1 and 2, 2 also present. Now this should not be transitive as well, right? So if we add 1, 1, this will become transitive. If we remove it, then the transitive nature will be lost. So what we did is, we just take this small set 1, 2, 2, 1. Now this is symmetric, obvious, because AB is there, BA is there. But if AB is there, BC is there, then CA is not there, right? So if 1, 1 is not there, therefore this is not transitive. Since 1, 1 and 2, 2 are not there, this is not reflexive. Reflexive. Right? But this is definitely a symmetric relation. Let's see the next part of the 10th question. We have to give an example of a relation which is transitive but neither reflexive nor symmetric. So it's again a very easy one. Let's consider a relation R is equal to AB such that A belongs to the set of numbers 1, 2, 3. Right? Similarly, B also belongs to the set of numbers 1, 2, 3. Right? So for this, like we did in the previous one, we have to prove, we have to take such a relation which is neither reflexive nor symmetric but transitive. Right? So not reflexive, not symmetric, but only transitive. So let's say we take a relation 1, 2, 2, 3, 1, 3. That's it. So in this, 1, 2 is there, but 2, 1 is not there, right? Therefore, this is not symmetric. Since 1, 2 is there, 2, 1 is not there, therefore this is not symmetric. Since 1, 1 is not there, 2, 2 is not there, 3, 3 is not there, therefore this is not reflexive. But this relation will be a transitive relation. So we all know why this will be a transitive relation, because 1, 2 is there, 2, 3 is there, and then similarly 1, 3 is also there. Now let's see the third part of this, which is the relation is reflexive and symmetric but not transitive. So this is also very easy one. Let's consider a relation R in set A. We'll take the same set 1, 2, 3. So we have to check for a relation which is reflexive, symmetric, but not transitive. So let's take 1, 1, 2, 2, 3, 3. Since all these three will satisfy the reflexive property. Now let's take 1, 2, 2, 1, and let's take just one more, or no need to take one more. That's it. We can just stop it here. And we'll observe that this relation is reflexive, this is symmetric, but this is not transitive. Since 1, 1 is there, right? 1, 2 is there. Then 1, 2 is there, this is true. Then 2, 2 is there, 2, 1 is there. Then 2, 1 is there, this is true. But this relation is becoming transitive. We have to prove that this is not transitive. So we'll have to add another set here. So let's say we take, so if we have 1, 2, let's take 2, 3 and 3, 2. Now this is perfect. So if 1, 2 is there, 2, 3 is there, then 1, 3 should also be present, but 1, 3 is not present in this, right? So 1, 2 is there, 2, 3 is there, but 1, 3 is not there. Therefore, this relation is not transitive. But this is a reflexive relation because of these three. This is a symmetric relation because of these two and these two pairs. So let's move on to the next part now. Next part is we have to check for a function which is reflexive and transitive but not symmetric. Similar example, let's say we take 1, 1, 2, 2, 3, 3. Let's take 1, 2, 2, 3, 1, 3. This is a pretty simple example. We have 1, 2, right? 2, 3, and we have 1, 3. This becomes a transitive relation. Similarly, we have 1, 1 and 1, 3, right? Then 1, 3 is present. Therefore, this becomes a transitive relation for sure. But this is not a symmetric relation because if 1, 2 is there, 2, 1 is not there. 2, 3 is there, 3, 2 is not there. Therefore, this is not symmetric. Reflexive, it will become from these three. Okay, this will contribute to the transitive property. But for symmetric, since 1, 2 is there and 2, 1 is not there, therefore this is not symmetric. Transitive and reflexive, it will be. So let's check for the fifth part, which is we have to check for a relation. We have to take an example such that relation is symmetric and transitive but not reflexive. So we'll take a simple example. Let's say we have 1, 2, 2, 1 and 1, 1. So this is a pretty simple example, right? 1, 2 is there, 2, 1 is there. Therefore, this is a symmetric relation. So 1, 2 belongs to R, 2, 1 belongs to R. Therefore, this is a symmetric relation. Now, 1, 2 belongs to R, 2, 1 belongs to R. Subsequently, 1, 1 also belongs to R. Therefore, this is a transitive relation. Right? Now let's check for reflexive property. So 1, 1 belongs to R, but 2, 2 does not belong to R. Therefore, the reflexive property is not satisfied in this question, right? So this is the perfect example which we can give, the simplest example which we can give, right? So I think you will be comfortable with these type of questions now. Let's move on to the next type. Next is, show that relation R in the set A of points in a plane given by PQ such that distance of point P from the origin is same as the distance of point Q from the origin, right? So we have to check for relation of points PQ such that the distance of P from origin is equal to Q from the origin. So we have to prove that this is an equivalence relation, right? Show that the set of all the points related to P is a circle passing through P with origin as center. Okay, this we can prove very easily. So first we'll check for reflexive property, right? So OP, which is the distance of P from the origin, will be equal to OP, right? So therefore, P comma P will belong to R. So therefore, this is a reflexive relation, right? To check for symmetric relation, if we have P comma Q belongs to R, this means OP is equal to OQ. So this implies that Q comma P also belongs to R, which means OQ is equal to OP. So this is also a symmetric relation, right? For transitive property, let's say we have PQ belongs to R, which gives me OP is equal to OQ. Next, let's say we take QS. This also belongs to R, okay, which means OQ is equal to OS. Now, if these two are true, we have to prove that P comma S also belongs to R. So this is very evident that this will also belong to R. Since OP is equal to OQ and OQ is equal to OS, OP will be equal to OS, right? So OP will be equal to OS, which proves that P and S also belongs to R. So therefore this is a transitive relation as well. So if these three properties are satisfied, therefore this will become an equivalence relation, right? So for the next part, let's see. Further show that the set of all the points related to point P is a circle passing through P with origin as the center. So we are taking all the points whose distance from the point P and O, right, is equal to the distance of that point from O, right? So this distance must be equal to this distance. This can become in a lot of cases, right? And this will give you a circle with O as the center and OP as the radius, right? And this circle will pass through P and Q and all the other points, right? Sorry. So therefore we prove that set of all the points related to P is a circle passing through P with origin as center. Let's move on to the next question. Next question is, show that the relation R is defined in the set A of triangles. All triangles R is equal to T1, T2, where T1 is similar to T2. This is an equivalence relation. So first we have to prove that this is an equivalence relation. We'll check for reflexive property. Now T1 and T1, these two will be similar, right? Actually they will be congruent. Now congruent triangles are also similar. If we take same triangle both times, then this will belong to the relation. So therefore this is a reflexive relation. Now for symmetric, if T1 is similar to T2, then T2 is similar to T1. This is pretty obvious. Therefore, this will satisfy the symmetric property as well. Let's check for transitive property. If T1 is similar to T2, if T2 is similar to T3, then this implies that T1 is similar to T3. So therefore this will also satisfy the transitive property. If these two triangles are similar, these two triangles are similar, then all these three triangles are similar to each other. Therefore the transitive property is also satisfying. Now next part we have to see which triangles among T1, T2 and T3 are related. So first triangle T1 has the sides 3, 4, 5. T2 has the sides 5, 12, 13. And T3 has the sides 6, 8, 10. Right? Now in the cases of T1 and T3, we can see that the ratio of sides of T1 and T3, this is equal to 3 by 6 equal to 4 by 8 equal to 5 by 10, which is equal to half. So these three sides are proportional to each other, and that's the property of similar triangles. If all the sides are proportional, then two triangles will become similar to each other. So therefore triangles T1 and T3 are related. Right? Now let's see the next question. Next question is quite similar to the previous one. Show that the relation R defined in the set of all the polygons P1, P2 such that P1 and P2 has same number of sides is an equivalence relation. Okay? What is the set of all the elements in A related to a right angle triangle with sides 3, 4, 5? So let's first check for reflexive property. We have P1, P1, right? Every polygon will have the same number of sides as itself, right? So this property is but obvious, therefore this will satisfy the reflexive property. Now for symmetric property, it's pretty obvious. Let's say number of sides of P1 is equal to number of sides of P2, right? Okay, I'll write this in subscript so that there's no confusion. So number of sides of P1 is equal to number of sides of P2, which means P1, P2 belongs to R. Now this will also mean that number of sides of P2 is equal to number of sides of P1, which gives you P2 P1 also belongs to R, right? So therefore this is also a symmetric relation. Now let's check for the transitive property. If n of P1 is equal to n of P2, similarly if n of P2 is equal to n of P3, this means that n of P1 will be equal to n of P3. So therefore the transitive property will also be satisfied. So therefore this is an equivalence relation. Now moving on to the next part, which is what is the set of all the elements A related to the right angle triangle T with sides 3, 4, 5. So let's suppose we have a right angle triangle with sides 3, 4 and 5, right? Now this polygon has 3 sides, right? So the set of all the elements in A related to this right angle triangle will be set of all possible triangles. Since all the triangles have 3 sides, therefore the number of sides of all the triangles will be equal to the number of sides of this right angle triangle. So this need not to be a right angle triangle, it can be obtuse angle, acute angle, right? All the possible triangles will come in this category, since number of sides is equal to 3, right? Moving on to the next question. L1, L2 is a relation such that L1 is parallel to L2. And L is the set of all the lines in XY plane. And this is a relation R. Show that R is an equivalence relation. Okay, this is pretty simple one. For reflexive property, we have L1 comma L1. So this is true, right? This belongs to R, since every line is parallel to itself, right? And next we have the symmetric property. If L1 is parallel to L2, this implies L2 is also parallel to L1. So therefore the symmetric property also satisfies. Now let's check for transitive property. If L1 is parallel to L2, L2 is parallel to L3, this implies L1 is parallel to L3. So this is also true, since if let's suppose this is L1, this is L2 and this is L3. Now L1 is parallel to L2, L2 is parallel to L3. Therefore L1 will be parallel to L3 as well. So therefore all the 3 properties satisfy. Therefore R is an equivalence relation for sure. Now we have to check set of all the lines related to the line y is equal to 2x plus 4. So in the chapter straight lines in 11th standard, we have studied all the lines parallel to a given line only differ by the constant value, right? So if we take y is equal to 2x plus c, right? This will represent all the lines which are parallel to this given line. So y is equal to 2x plus c, where c belongs to real numbers, this will give you all the parallel lines which are related to this line, right? So I've written c belongs to real number, the full form, because If I wrote R, it will be confusing to the relation. That's why I've written it like that. So this is a pretty simple question. Let's move on to the next question. So next one is, let R be a relation in the set 1, 2, 3, 4 given by 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 2, 3, 3, 3, 2. Choose the correct answer. R is reflexive and symmetric but not transitive. R is reflexive and transitive but not symmetric. Symmetric and transitive but not reflexive. R is an equivalence relation. So we can easily check for that. First check for the reflexive property. So for reflexive property, 1, 1, 2, 2, 3, 3, and 4, 4. All of these should be present in R. And they are actually present in R. We can actually see that. That 1, 1, 2, 2, 3, 3, 4, 4 all are present. Therefore, this is a reflexive relation. For symmetric nature, we have to see that we have 1, 2 belongs to R. But 2, 1 does not belong to R. Therefore, this is not a symmetric relation, right? Now, let's check for all the transitive properties in this. So we have 1, 2, 2, 2, and then we have 1, 2 again. So this is transitive in that case. Similarly, we have 1, 3, 3, 2. So if we have 1, 3, 3, 2, we should have 1, 2 again, which we have. This is true, right? Next, if we check for all the possible transitive triplets, then it will be true for all of them, right? So you can easily check for the transitive nature. It will come out to be transitive. So therefore, this is reflexive and transitive but not symmetric. So B option will be correct in this case, right? So moving on to the last question. Let R be a relation in the set N given by R is equal to A is equal to B minus 2, where B is greater than 6. Choose the correct answer. Okay, so we have to check which will satisfy this relation. So for the first case, 2, 4. This gives 2 is equal to 4 minus 2. So this condition is 2, but 4 is not greater than 6. So therefore A part is not correct. Let's check for B part. So for 3, 8, 3 is not equal to 8 minus 2. Therefore, this is again false. Therefore, this is false. For C part, we have 6 is equal to 8 minus 2, right? Now in this case, this value of B, which is 8, this is greater than 6. Therefore, both conditions will satisfy. Therefore, C part will belong to this relation. Now let's check for D part. We have 8, 7. So if we put 8 is equal to 7 minus 2, this is not true. 8 is not equal to 5. Therefore, this will also not satisfy. So the only solution in this case will be C part. So this was the 16th question we had. So that's all from my side. So this was the complete solution of exercise 1.1 of relation and functions. Stay tuned for more. Thank you.